When people ask me why Mars lost its atmosphere, they usually expect a local story. They expect an answer about volcanoes shutting down, or the magnetic field collapsing, or the solar wind stripping gas away. All of that is part of the picture. But I want to place Mars into a much larger context. Mars is not just a failed Earth. It is a small world embedded in a gravitational field, inside a star's radiation, inside a galaxy full of dark matter, inside an expanding universe driven by dark energy. To really understand why Mars looks the way it does today, I have to connect the local physics of air molecules and magnetic fields to the cosmic physics of gravity, space-time, and the long-term evolution of the universe. I will keep the language simple, but I will not simplify the science to the point where it becomes wrong. I start with what we observe. Mars today has a very thin atmosphere. At the surface, the pressure is less than 1% of Earth's sea level pressure. It is mostly carbon dioxide with traces of nitrogen and argon. There is almost no oxygen. There is very little water vapor. The sky is dusty and the air is cold. Yet the surface shows clear evidence that this was not always the case. We see dried up river valleys. We see delta-like structures where rivers once flowed into standing bodies of water. We see minerals that form in the presence of liquid water over long times. We see layered sediments that look like lake beds. These features tell me that early Mars had liquid water on its surface for extended periods. Liquid water at the surface demands higher pressure and a warmer climate. So Mars must have had a thicker atmosphere in the past. The core question is, where did that atmosphere go and why? To answer that, I need to think about gravity first. Gravity is the basic reason any planet can hold an atmosphere at all. In the modern view, following general relativity, gravity is not a force in the old Newtonian sense. It is the curvature of space-time caused by mass and energy. Mars, like Earth, curves space-time around it. Gas molecules follow paths in this curved space-time. In practice, for a planet, I can still use the simpler Newtonian picture. The planet pulls on the gas molecules, and if those molecules do not move too fast, they remain bound. The escape velocity at the surface of Mars is about 5 kilometers per second. On Earth, it is about 11 kilometers per second. This difference matters a lot. The thermal speed of gas molecules depends on temperature and molecular mass. At a given temperature, lighter molecules like hydrogen and helium move faster than heavier ones like nitrogen and carbon dioxide. If the typical speeds of molecules are a significant fraction of the escape velocity, some will sit in the high-speed tail of the Maxwell-Boltzmann distribution and leak away into space over time. This process is called thermal escape, or Jeans escape. Because Mars has lower gravity, its escape velocity is lower, so it is easier for gas molecules, especially light ones, to reach escape speed and leave. We know this is not just theory, because we have direct measurements. Orbiters like MAVEN, the Mars Atmosphere and Volatile Evolution mission, have measured how particles escape from the Martian atmosphere today. They see ions and neutral atoms streaming away, accelerated by interactions with the solar wind and by the planet's own upper atmospheric processes. By measuring the rates of escape for different species, and by using models of the past solar output, scientists can estimate how much atmosphere has been lost over billions of years. These estimates are consistent with the idea that Mars once had a much thicker atmosphere. So gravity sets the basic vulnerability. Mars started with a disadvantage. It sits in the same gravitational field of the Sun, but its own gravitational well is shallower than Earth's. However, gravity alone does not explain the rapid loss. Venus has a gravity similar to Earth, but a very thick atmosphere. Mars has lower gravity, but the scale of loss suggests an additional factor. This brings me to magnetic fields and the solar wind. The Sun is not a quiet ball of light. It emits a continuous flow of charged particles called the solar wind. These particles carry energy and magnetic fields. When the solar wind hits a planet, it interacts with the planet's own magnetic field, if it has one, and with its upper atmosphere. Earth has a strong global magnetic field generated by a dynamo in its liquid outer core. This field creates a magnetosphere that deflects most of the solar wind around the planet. Some charged particles still get in at the polar regions and cause auroras, but the bulk of the atmosphere is shielded from direct impact. Mars today does not have a global magnetic field. Instead, it has small crustal magnetic patches, remnants of an earlier dynamo. The evidence from these crustal fields and from the planet's internal structure suggests that Mars once had a molten, convecting core that generated a global magnetic field, similar in principle to Earth's. At some point, that dynamo shut down. The core cooled, convection slowed, and the field weakened and eventually disappeared. Without a global magnetic shield, the solar wind could interact directly with the upper atmosphere of Mars. Charged particles from the sun could pick up atmospheric ions and drag them away. This is called ion pickup and sputtering. High-energy particles can also knock atmospheric atoms out into space by direct collisions. MAVEN has seen these processes in action. It has measured how the solar wind strips ions from Mars today, especially during solar storms when the sun's activity spikes. The timing is important. Young stars, including the young sun, are more active. They emit stronger ultraviolet radiation and more intense solar winds. So early Mars was exposed to a harsher environment at the same time as its magnetic field was weakening and disappearing. This combination is efficient at removing atmosphere. Models that include the history of the sun's output, the timeline of the Martian dynamo, and the physics of atmospheric escape can reproduce a scenario where Mars goes from a thicker, warmer atmosphere to the thin, cold one we see now over a few 100 million to a billion years. That is still a long time in human terms, but it is fast on planetary timescales. At this point, I have a local story. Low gravity, loss of magnetic field, strong early solar wind, and atmospheric escape. But I also want to connect this to the larger gravitational environment of the solar system and the galaxy. Mars does not orbit in a vacuum. It moves through the gravitational potential of the Sun, which itself sits inside the Milky Way's gravitational field, which is dominated by dark matter. Dark matter does not interact with light, but it does contribute most of the mass in the galaxy. We infer its presence from the rotation curves of galaxies, from gravitational lensing, from the cosmic microwave background, and from large-scale structure. In our galaxy, dark matter forms a roughly spherical halo that extends far beyond the visible disk. The Sun, Earth, and Mars all orbit within this halo. Does dark matter affect Mars's atmosphere directly? As far as we know, no. Dark matter interacts with normal matter primarily through gravity, and the density of dark matter in the solar neighborhood is very low, about 0.3 Gs per cubic centimeter, which is roughly 5×10^-25 kilograms per cubic meter. That is many orders of magnitude less dense than air or even interplanetary gas. A Mars-sized planet moving through this dark matter halo feels a tiny additional gravitational influence, but it is effectively constant and acts on the whole solar system. It does not strip atmospheres or erode surfaces. However, dark matter did matter when the solar system formed. The distribution of dark matter in the early universe helped seed the formation of galaxies and set the gravitational wells in which gas could cool and form stars and planetary systems. Without dark matter, the density fluctuations we see in the cosmic microwave background would not have grown fast enough to form galaxies by today. So indirectly, dark matter is part of the reason there is a Sun, an Earth, and a Mars at all. Dark energy plays a different role. Dark energy is the name we give to whatever is causing the accelerated expansion of the universe. We infer its existence from observations of distant Type 1a supernovae, from the cosmic microwave background, and from the large-scale distribution of galaxies. The best current model is that dark energy behaves like a cosmological constant, a uniform energy density filling space, causing spacetime to expand faster on large scales. On the scale of the solar system, and even on the scale of galaxies, this expansion is negligible. Gravity from the sun and the galaxy holds these systems bound. The expansion of the universe is significant only on scales where gravity is weak and matter is spread thinly, such as between galaxy clusters. So dark energy does not directly pull Mars's atmosphere apart. It does not stretch the planet. The gravitational binding of the planet and its atmosphere easily wins over the tiny effect of cosmic expansion on those scales. Still, I find it useful to keep the cosmic expansion in mind. It reminds me that Mars is evolving in a universe that itself is evolving. The young universe was denser, hotter, and more uniform. Over time, gravity amplified small fluctuations in density into galaxies, clusters, and large-scale structure. Dark matter dominated that process. Later, as the universe expanded and matter thinned out, dark energy began to dominate the dynamics of accelerated expansion. The solar system formed about 4.6 billion years ago, when the universe was roughly 2/3 of its current age. By then, dark energy was already present, but not yet as dominant as it is today. The conditions in the galaxy, including the rate of nearby supernovae, the metallicity of the interstellar medium, and the local radiation environment, were all set by this cosmic history. Those conditions influenced the composition of the protoplanetary disk from which Mars formed. That composition, in turn, set how much volatile material like water and carbon dioxide Mars could accrete or outgas. Now I go back down to the planet. The amount of atmosphere a planet has is a balance between sources and sinks. Sources include outgassing from the interior through volcanism, delivery by comets and volatile-rich asteroids, and in some cases, chemical reactions that release gases from rocks. Sinks include escape to space, chemical reactions that lock gases into minerals, condensation and freezing, and impacts that can blow atmosphere away. For Mars, we have evidence of large volcanoes, such as Olympus Mons and the Tharsis region, which suggests that in the past Mars was volcanically active and likely outgassed significant amounts of CO2, water vapor, and other gases. But Mars is smaller than Earth. Its surface area to volume ratio is higher. It loses internal heat faster. As a result, its mantle convection slows more quickly, its core cools faster, and its volcanism declines earlier. This means the source of new atmosphere from the interior weakens over time. Meanwhile, sinks remain. Atmospheric escape to space continues, especially without a magnetic shield. CO2 can be locked into carbonate minerals. Water can be lost to space as hydrogen escapes and oxygen is bound into rocks. Some water is still present as ice in the polar caps and in the subsurface, but much of the original inventory is gone or sequestered. Impacts early in Mars's history could also have removed atmosphere. Large asteroid or comet impacts can heat the atmosphere and accelerate gas to escape velocity. Whether they are net sources or sinks depends on the details. They can also deliver volatiles. The early solar system was a violent place, with frequent large impacts. Over time, this bombardment calmed down. We know much of this not just from theory, but from multiple lines of evidence. We have in situ measurements from landers and rovers of atmospheric composition, isotopic ratios, and surface minerals. For example, the ratio of heavy to light isotopes of elements like nitrogen and argon in the Martian atmosphere is higher than in Earth's atmosphere or in the Sun. This is a signature of loss. Lighter isotopes escape more easily, leaving the atmosphere enriched in heavier isotopes. MAVEN has measured these ratios and used them to infer the integrated loss over time. We also have Martian meteorites that have landed on Earth. Some of these contain trapped gas bubbles whose composition matches the Martian atmosphere. By measuring their ages and their isotopic composition, we can reconstruct parts of Mars's atmospheric history. Orbiters use spectroscopy to map minerals and ices, revealing where water once flowed or pooled. All of this builds a consistent picture. Early Mars was wetter and had a thicker atmosphere. Over billions of years, it lost most of that atmosphere through a combination of low gravity, magnetic field loss, solar wind stripping, thermal escape, and chemical sequestration. Where do dark matter and dark energy enter this story in a more subtle way? They set the boundary conditions for everything. Dark matter determined how quickly structures like galaxies formed. That, in turn, influenced when and how the heavy elements needed for rocky planets were produced in stars and spread into space. Without dark matter, the universe's expansion, even without dark energy, would have diluted matter so quickly that galaxies and stars would have struggled to form on the observed timescale. Dark energy, by driving late-time acceleration, influences the long-term future. It means that in the very distant future, galaxies outside our local group will recede beyond our observable horizon. The large-scale structure will thin out. But on the timescale of Mars's atmospheric evolution, dark energy is just a constant background term in the cosmic equations. It does not alter the local gravitational binding of Mars's sphere. However, the fate of the universe and the fate of planetary atmospheres are connected conceptually. Both are about the competition between gravity and expansion, or between binding forces and processes that disperse matter and energy. For Mars, the binding is its own gravity and, in the past, its magnetic field. The dispersing processes are thermal motion, solar radiation, and the solar wind. For the universe, the binding is gravity from matter and dark matter, pulling structures together, while the dispersing process is the expansion of space-time driven by dark energy. On small scales, gravity wins. Planets, stars, and galaxies stay bound. On the largest scales, dark energy wins. The distances between galaxy clusters grow faster and faster. There is an analogy here, but it is limited. The physical mechanisms are different, but the mathematical language of potentials, energy densities, and escape conditions appears in both. If I imagine the far future, the Sun will eventually leave the main sequence. In about 5 billion years, it will expand into a red giant. Long before that, its luminosity will increase enough to make Earth and Mars warmer. On Earth, this will likely lead to a runaway greenhouse and the loss of oceans. On Mars, the increased solar flux might temporarily warm the surface, but by then Mars will still have low gravity and no global magnetic field. Any new atmosphere or released volatiles will again be vulnerable to escape. On longer timescales, after the Sun becomes a white dwarf, both Earth and Mars will be cold, airless, or nearly airless rocks orbiting a faint remnant star. The accelerated expansion of the universe will continue, driven by dark energy, but the local gravitational binding of the solar system, now a white dwarf and its planets, will remain unchanged by that expansion. There is a deeper question about gravity itself that touches Mars indirectly. General relativity describes gravity as space-time curvature. It has passed all local tests with high precision, but we still do not know how to unify gravity with quantum mechanics. We do not know the true nature of dark matter. We do not know what dark energy actually is. It could be a cosmological constant. It could be a field that evolves slowly. It could be a sign that our theory of gravity needs modification on large scales. These uncertainties do not change the basic story of Mars's atmospheric loss, because the gravitational physics at planetary scales is well tested. But they remind me that our understanding of gravity, space-time, and the cosmic context is incomplete. If in the future we discover that gravity behaves differently on very large or very small scales, we will need to re-examine many assumptions, including some of the early solar system and the formation of planets. When I look at Mars as a case study, I see a planet that sits at the edge of habitability. It is large enough to have had volcanism and a substantial early atmosphere, but too small to hold that atmosphere for the age of the solar system under the assault of the solar wind. It formed in the same protoplanetary disk as Earth, under the same galactic and cosmological conditions, in a universe shaped by dark matter and dark energy. Yet small differences in mass, distance from the sun, and internal dynamics led to very different atmospheric outcomes. We can test our understanding of atmospheric loss by comparing Mars with Earth and Venus. Venus has a thick, hot atmosphere dominated by CO2, with a runaway greenhouse effect. Earth has a moderate atmosphere, protected by a magnetic field and regulated by plate tectonics and a carbon cycle. Mars lost most of its atmosphere and became cold and dry. These three worlds in the same stellar system give us three different solutions to the same underlying physical equations. We know a lot about Mars's atmospheric loss, but there are still open questions. We do not yet know the exact timeline of the magnetic field's shutdown. We do not know the precise initial inventory of volatiles Mars started with. We do not know how much atmosphere was lost in catastrophic events like large impacts versus steady, continuous escape. We do not know how long stable surface liquid water persisted and whether it was episodic or continuous. These uncertainties matter for understanding whether Mars ever had conditions suitable for life and for how long. They also matter for comparing Mars to exoplanets. Many exoplanets we find are close to their stars, exposed to strong stellar winds and radiation. Their ability to hold atmospheres depends on mass, composition, magnetic fields, and stellar activity. Mars is our nearby laboratory for testing atmospheric escape processes in detail. So I end with a specific open question tied directly to the science. How much of Mars's original atmosphere was removed by solar wind stripping after the global magnetic field collapsed? And how much was lost earlier through impact erosion and thermal escape before the dynamo shut down? We have partial answers, but not a complete, precise budget. Solving this will require better constraints on the early sun, a clearer history of Mars's interior and magnetic field, more detailed isotopic measurements, and perhaps future sample return missions. Until we can close that budget, the exact story of how Mars went from a thicker, warmer atmosphere to the thin air we see today remains an active and important mystery.